Okay, this is video 1 of light, boys and girls. So today, we're starting a unit on light. So I'm sitting in the dark in my house right now, and using this flashlight, kind of looking around, see what's happening. And we're going to kind of talk about light a little bit. Illumination, how light works, what light is. That's the next unit we're going to be dealing with, is kind of light and color and stuff like that. And then we'll talk about lenses and refraction and how light bends, and we'll talk about mirrors and stuff and how that works, and just kind of why light behaves the way it does. Okay? So here's what we're going to do. We're going to first talk a little bit about just generic stuff about light. What is light? What's it made of? How does it travel and stuff like that? The dark's kind of helpful in seeing some of this, so that's kind of why we're doing it this way. And this is just kind of fun. I obviously need a haircut. But that's what we're going to do. We're going to look at light, okay? So let's talk about light just at first. What is light? How does it travel? How does it work? Light's kind of baffled people for a long time. And people, of course, took it for granted like they did everything else, and never really thought a whole lot about it for years. And then people came along and started wondering, okay, well, where does it come from? Well, it comes from the sun. How do we reproduce it? Well, we can use fire. Eventually burning things, like a filament in a light bulb, which Thomas Edison came out with or came upon. And now we use excited gases. All those noble gases that are in the last column, or column 18 of the periodic table, are a lot of times used for different colors of neon lights and stuff like that. And fluorescent lights are again using excited gases, and you're seeing electrons jumping is moving energy levels, and that's kind of how you end up with the light that we get out of fluorescent lights. So that's what's going on. But it's taken a long time to get to the point where we understand it to where we do like that. So here's just kind of an introduction to what we're going to be talking about. Okay. First off, light moves in straight lines, and it moves at about 300 million meters per second, or 300,000 kilometers per second. That would be, about 3 million football fields in 1 second. It's a long way, and it moves very, very quickly. Obviously, give you a little bit of perspective. It would take roughly around 8 minutes or so for us to figure out that the sun had stopped producing light if it went out. That's how far away we are. If you took the 300 million meters for every second for that 8 minutes, and you multiply the 300 million per second there for those 8 minutes, that would give you a rough estimate of how far we are from the sun. A long way. And obviously light travels very, very, very quickly. So, and it travels in a straight line. Those are key things that we need to remember. So the value, 300 million meters per second, as well as the straight line. Okay? All right. So as light's traveling, kind of an interesting thing about light is it behaves like a wave and it behaves like a particle. Okay? It does both. Einstein came along and came up with his photoelectric effect, and that's where he got his big notoriety. We've talked a little bit about him and how that happened, and we all know, yes, he's known for theory of relativity and all that, but really it's his photoelectric effect that put him on the map, and that's what got him noticed in the early 1900s, being a patent clerk up in Austria. He got his notoriety by writing 4 papers, one of which was photoelectric effect, and that was the one that really people noticed. And so what happened is he began to look at this idea of light either being a wave or being a particle or both, and he said that yes, it was both, and that was kind of a novel concept. There were people who were arguing both sides, and he was able to provide proof that yes, it was both. And basically he said what happened is through reflection, whenever light hits shiny surface, it's ejecting photons, and we get these photons, or these little packets of energy, these particle-like, but it's traveling along a wave, an electromagnetic wave. And we know electromagnetic waves are the only type of wave, as we've studied sound and other waves already, but electromagnetic waves are the only waves that can travel in a vacuum. It does not require a medium. It's not a mechanical wave. So we get these electromagnetic waves from the sun. They heat the earth, they provide us light, and we don't have to have something to carry them from there to here. The particle itself is what does that. Okay. All right, so just a little bit of, kind of a basic idea of light. And it is energy. It's energy traveling in an electromagnetic wave. Now, another cool thing about light is there's something called, there's kind of an inverse square rule with light, okay, based upon distance. We've talked about inverse square rules, inverse square laws with things such as gravity and with Coulomb's law and stuff like that. We've dealt with a lot of inverse square law stuff already. But light kind of behaves the same way. See, if I shine this light back here towards the back of my room, I'm in my, kind of our library room at our house. We got a bunch of C's on that wall for obvious reasons. And the lone U, my wife's maiden name started with a U, so there's a U sitting back there by itself. But I can shine this light back there, and what's going to happen if I walk closer to the wall? Either kind of pause the video, think about it for a second, answer, or if you already know the answer, let's kind of see if you're right. What do you think is going to happen? Okay, let's test it out. Okay, as I'm walking closer, the pattern's getting smaller. And it gets very, very, very small the closer I get to the wall. And it widens out. It gets larger and larger and larger. But what happened to the brightness? Obviously, it's not nearly as bright as it was. So what happens is, see what's going on, is that energy takes and spreads out over a larger area the further you go. Like what happened when we talked about sound. Remember how we talked about sound being like a sphere, and as it moves out like a balloon, that balloon or latex gets thinner and thinner. That's what's happening with the energy of the sound wave. It's getting thinner and thinner and thinner and spreading out. That's what's happening with light as well. It's the same amount of energy if you're close up. It's just condensed and very, very, very small, so it's very bright. The further you go, it spreads out larger. And so what happens is, it's kind of exponential. If you double the distance, that area then is twice as wide and twice as tall. So by doubling the distance, you've made it twice as wide and twice as tall. So how do we get area? It's length times width, right? Or base times height. So 2 times 2 means it's now spread out over 4 times the area. So the energy there per square meter or whatever is 1/4 of what it was. You move 3 times back. It's 3 times as wide, 3 times as tall. Now it's spread over 9 times as large of an area. So the energy is going to be 1/9 as much per square meter. If you take the whole, it's still the same amount of energy. But for the single meter, it's 1/9. Move back 4 times, 16th. 5 times, 25th. 6 times, 36th. It continues to be an exponential loss. Okay? And in reality, it not only decreases as it spreads out, but yeah, the light actually gets absorbed into other stuff too. little particles of fuzz. Um, anything that's being heated up, that energy is going to go into heat, right? So it kind of warms a little bit too, so you're losing some energy there. And that's why, like, if you were to shine a light up into the sky, it may go a long, long, long way, but it's not just going to keep on going forever, because eventually it kind of, those particles, as it spreads out over a huge, wide area, those particles still absorb stuff too. Okay? Lasers, a great example of keeping a concentrated area. And if you want to kind of do an interesting little thing, I want you to look up what does laser stand for? What's the acronym of laser? Because it's not just a word. LASER actually stands for something. So take a look at that. I want you to look it up. I'll probably ask you about it in class when we're kind of working on stuff. Okay? All right. That's the end of this video. We'll do some others about mirrors and stuff like that. Okay? Thanks.